Okay, so in the previous video, we were able to relate the entropy of a system to something that we called a microstate. In fact, we can actually write an equation for this, where the entropy is going to be equal to a constant, which is called the Boltzmann constant, times the log of the number of microstates. Okay, W being the number of microstates. Now this is a useful equation, don't get me wrong, but the fact of the matter is when we're dealing with chemicals, we're never dealing with four particles. Okay, so computing the actual number of microstates just from scratch is a very difficult thing to do in chemistry. So instead of that, what we look for are properties that indicate an increase or a decrease in entropy. So generally speaking, okay, the more static something is, the lower its entropy. Okay, so for example, if we were comparing a solid to a liquid, okay, we would say that in the solid we have all the particles kind of packed together in this regular repeating pattern. If we needed to, we could pinpoint one of those atoms if we really wanted to. Whereas in a liquid, the particles are close together, but they're moving past one another. So keeping track of one of those particles would be very difficult. Okay, so what we can say here is that a solid has a lower entropy than a liquid. Now, if we compare a liquid and a gas, okay, here we have, liquids which have particles that are moving around, but a gas where we have particles that are literally bouncing off each other and not even touching one another for the most part. The gas is going to have a much greater entropy. Okay, and therefore we would expect the entropy of a gas to also be greater than that of a solid. Okay, and we find that while solids have less entropy than liquids, they are far more similar to one another than either one of them is to a gas. Gases have lots of entropy. Okay, other things that can lead to increases in entropy are an increase in temperature. If you increase the temperature, that leads to an increase in the velocity of the particles that are present, which makes them more difficult to keep track of. Okay, therefore, they have greater entropy. Okay, if we perform a process that produces gas molecules, so if we have a net increase of gas particles, okay, that will be accompanied by an increase in entropy. Okay, so generally speaking, the more difficult it becomes to locate a particular particle, the greater the entropy that it has. Okay, now why is this important? Well, we have these things called the laws of thermodynamics. Okay, and there are three of these laws. The first one we introduced back in Chem 101. Okay, and that was that the energy of the universe is constant. Okay, and from that we were able to derive an equation like this, where we said the delta E of the universe was equal to 0. Okay, and we could also use that to relate to the changes in the energy of the universe, which is 0, to the energy changes in a system versus its surroundings. Now, the second law of thermodynamics deals with entropy. And basically what this says is that the entropy of the universe increases. I'm sorry, the change in the entropy of the universe will always increase. Okay, and we can formulate that as the delta S of the universe is always greater than or equal than 0. Okay, so whatever happens in a reaction flask has to lead to the overall universe increasing in entropy. Okay, which sounds like a kind of a tall order there, but we'll talk about that more as we continue on here. Okay, the last law of thermodynamics is that a crystal, I'm sorry, a perfect crystal at 0 Kelvin has no entropy. Okay, another way of saying that is that if I had this perfect crystal, say like I had a diamond, diamonds are made entirely of carbon atoms. Okay, so if this diamond is absolutely pure, and that means there are no other atoms present, and there is this perfect, regular, repeating lattice. Okay, so we know exactly where all the atoms are, and it's at 0 Kelvin where we have absolutely no motion whatsoever, then there is no entropy. And what's interesting about that is that this really sets entropy apart from enthalpy, in that enthalpy was measured relative to kind of a arbitrarily chosen reference point, which was that the enthalpy of formation for any substance in its or any element in its standard state was equal to 0. Here, entropy is actually absolute. Okay, again, very different from enthalpy in that regard. Okay, so from here we'll look at some of the implications of these laws and how they impact chemical reactions.